Hello, we are going to talk about a very important aspect of the laser or a characteristics which is called coherence. Now, coherence is believed to be this physical characteristics of the laser which involves something being in phase or in step with each other. That is indeed the idea, but this is captured succinctly by the definition of coherence, which basically is a statement on correlation of the electric field between two spatio-temporal points. So let me illustrate that. So let's say I'm looking at the electric field associated with the laser light at a location R1 at a time t1, and I'm interested in what is the correlation of this electric field with the electric field at another space point R2 at another temporal point t2, and such an object, this is the electric fields are in the complex notation, and such an object when averaged over an ensemble of such measurements or such possibilities would actually present a non-zero number, and if this number is non-zero, then one says that there is finite coherence. These brackets, let me be careful, this is an ensemble average. I will focus myself to the final result of such a calculation. So when we look at coherence, this is also called the first order correlation or first order coherence. Now when we look at coherence, one can easily now split this into two different aspects. That is, what I'm going to do is I'm going to focus myself at a specific point. Let us keep that spatial location R to be fixed, and I can look at the electric field correlations which are happening at that same location R at a time t2. That is, I am relating the electric field which is at a time t1 with the electric field which is coming after a certain time, for example at time t2, and ask, is there any relationship between these two quantities? It is very clear that if the field is randomly fluctuating, and once I take an ensemble average, this averaging process, if the underlying fields are all random, is going to turn out to be zero. It is only when you have some definite relationship that you would see that this quantity turns out to be finite. So imagine that the difference between the time which I am looking at is t2 minus t1, let me call the delta t, and as I increase this time delta t, I would see that the phase relationships between the fields starts to disappear. So obviously there is a time delta t, okay, which I am calling it as delta tau, which I am calling as coherence time, within which the fields remain correlated. After calculating this for quasi-monochromatic fields, which I am not going to undertake the calculation, but you can for example refer to the book Optics by Eugene Hecht, and there is a nice derivation for this. So this delta tau, which is the coherence time, is inversely proportional to the bandwidth of the light that is coming. That is, if I am having an absolutely single frequency emission, that would mean that my delta nu is approaching zero because there is no width, but it's a precisely single frequency content of the light. I would have infinite coherence time. The way to understand this physically, you can do a small exercise and figure this out. Let's imagine that I am having a wave which I am drawing in time. Imagine this is a perfectly sinusoidal wave, right? And this extends all the way from minus infinity to plus infinity, the spectral content of this monochromatic wave would be represented by a delta function, right? That is, if I plot the power versus frequency of such a wave, I would be hard pressed to give it a finite width. So what I would see is there is zero frequency content, and precisely at one point there is finite power, and this is precisely the frequency of this monochromatic wave. So if you think of another situation where I have a similar wave, but now rather than having it extended from minus infinity to plus infinity, imagine that this wave is finite, right, within a finite time period, let us say delta t. Now I can clearly see that if such a wave exists, then the very fact that I have curtailed or have cut the wave into a finite wave train or a duration, in this situation, the corresponding spectrum that I would get would be actually something broadened, where this width of this spectrum would largely go as 1 over delta t. That is, if the extent of the wave is extremely large, like in the previous scenario, I would get essentially an extremely narrow spectrum. But as I cut this wave to finite size, I would start seeing now a power which is broadened about, again, the central frequency nu naught, but then because we have cut it down, one would see this broadening of the spectrum. You're familiar with this kind of analysis using Fourier transforms. You can clearly see that if the wave is completely monochromatic, in that situation, one can relate any point in time, given that there is a certain amplitude at a particular point, one can predict at any other point what exactly the amplitude is going to be, and there's going to be a definite correlation between these two. So for example, if the phase difference between them is, let's say, 20 pi, at a later time, as this wave moves around, irrespective of what the wave is, because it's perfectly monochromatic, you would actually see that there is a correlation between these 2 points in time, and the phase difference is definite in terms of 20 pi. So one can think of it another way, that is, in comparison to an infinite wave, if one wants to construct a finite wave train, I need to add multiple Fourier components. That is precisely what I have done here. I have looked at various Fourier components which need to be added, right, so as to create this finite wave train. And that would mean that if I come up with a light which has got multiple Fourier components, then that would imply that it would result in a notion of a definite phase only within a time period delta t, and beyond that time period delta t, one would see that the waves will get out of step, or there will be no relationship between phases, amplitudes and phases of light between these two temporal points, right? So how does one go about now trying to measure such a property of the laser, or for that matter of any source? So what one does is to utilize interferometers to make these measurements. So the interferometer that we are going to look at for measuring the coherence time, it basically, in one arm of the interferometer you have a field, and what you do is overlap that field with the field that is coming from the other arm, wherein there has been a certain time delay. So by adjusting the length of the arm, or the relative time delay between the two paths the light takes, one would be able to overlap them and look at a formation of a fringe pattern. So let me just quickly draw the interferometer, and this interferometer is the Michelson interferometer. So idea is simple. So what I have is a source, light is coming in, and the light falls on a beam splitter, right, in such a manner that it partially reflects and partially transmits. And then each of these beams, the path 1 for example faces a mirror. This is mirror 1. This is the beam splitter, and the path 2 again faces another mirror, M2. And you see that this light that goes reflects back from that mirror. This light reflects back from this mirror. And then they again meet at the beam splitter, wherein, so one of the original beam had suffered a reflection and a transmission across the beam splitter. Now the reflected beams suffer exactly the opposite. So the one which suffered the transmission suffers a reflection, and it comes down here. The one which suffered the reflection first now suffers a transmission and comes down here. So these two beams overlap, and what we get is basically a fringe pattern between these two fields. That is, what I'm going to do is, so let me carefully denote a few things. Let's say this length was D2. This length on the other hand is D1. So you see clearly the difference in the path taken is given by 2 times D2 minus D1. The factor of 2 comes because the light traverses this path twice, right? And if I am looking at what is the time difference or time delay between the two beams, then the delta t is given by twice d2 minus d1 divided by c, where c is the speed of light, right? So clearly this is the path difference between the two. So if I now plot visibility of the fringe pattern, right, with this path difference delta t, which essentially is equivalent to moving one of the mirrors with respect to the other. So what I get is basically a curve, something of that kind, where this value is, let's say, 1 and this is 0, and so there is some notion of a, I can come up, and this location is what I call tau c, or the measure of temporal coherence. So let me again be complete. What I mean by visibility is that I look at a fringe pattern, I look at the maximum intensity which is there, so, and I subtract it with the minimum intensity which is there. Remember, in fringes you have maxima and minima, and then divide by the sum of the two. You can clearly see that when I don't have fringes, that is there are no regions of maxima and minima, that would mean my I max is equal to I minimum, and then the visibility would be 0. Whereas when I have very sharp or very well-defined fringes where my I minimum is 0, I would see that this quantity goes to 1. So this quantity visibility is essentially contained between 0 to 1. So you can think of this arrangement in this fashion, that the input light consists of wave trains, like the wave trains that we have discussed earlier, and part of the wave train gets reflected in both the arms. Now you see that the phase relationships are definite only within the wave train. So if I now overlap parts of the wave train, I would get a definite fringe pattern. But as I increase the delay between the light, between the two, one of the wave trains overlaps with another wave train which has no uh, definite phase relationship with the previous one. In that situation, clearly you will see that my fringe pattern disappears, and this is precisely what you see uh, here, wherein you see that as you increase the path difference, that is my delta tau, the visibility starts decreasing and goes to zero. So this measure of finite visibility is essentially, this tau c is related to how monochromatic the beam is, right? It's inversely proportional to the bandwidth of the incoming light. So when I say that laser light is extremely monochromatic, that would mean that I can now, with a laser beam, I can create an experiment in which I can hope to overlap two beams of radiation. If it's well within that spatial length scale, I would get constructive and destructive interference. But if you go beyond this length scale, in that situation, the fields will overlap and basically not be able to create an interference pattern that neither a bright or a dark fringe, but what you get is basically a homogeneous illumination of the field of view from such an interferometer. Yeah, so let us now look at this whole business a little mathematically. So, okay, so basically what I have is a function of time, which represents, for example, the electric field. And this is a function which is at a definite frequency. Let me call it I omega naught t. That's with a unit amplitude. And this is between for a time duration of tau naught, within the times minus tau naught by t to tau naught by 2, and it is 0 elsewhere. Right? This is my function. And now what I'm going to do is I'm simply going to take the Fourier transform of this finite wave train and compute and see what you get, right? So I'm sure all of you can do this. I'm writing down the Fourier transform g of omega, which is simply 1 over 2 pi. I'm now integrating from minus infinity to plus infinity. This is my definition for the Fourier transform. If I do this, if I implement this, I would essentially get the sinc function, right, which will be exponential I omega minus omega naught t divided by 2 pi I. I have to put in the limits from minus tau naught by 2 to plus tau naught by 2. Now if you rewrite this, what you get is essentially this function, which is tau naught by, I multiply and divide by tau naught and write this in terms of sine u over u, right? Where I have taken my u to be omega minus omega naught times t. So if I plot this function, what I would get is essentially there is going to be a central lobe. So the first zero of this is going to come out at 2 pi by tau naught, and you can clearly see that as my tau naught becomes smaller, right, this whole spectrum is going to widen, and essentially this width is essentially uh, goes like pi by tau, right? So So you can clearly see that my spectral line, that is my delta nu associated with my light beam, right? This is the most important characteristics, and this delta nu basically goes like 1 over tau naught, where tau naught is now the duration of the finite ray. Now let us be very careful. This is 2 pi by tau naught. Recall we had delta omega as 2 pi by